Hi everyone. That previous videos we discussed Nmr Spectroscopy. Now I'll continue for that. Some important NMR chemical shift selected compounds containing heteroatoms. We consider that alcohol molecule. What is the chemical shift? That here 3.39. That ethyl alcohol, isopropyl alcohol, tertiary butyl alcohol. These are all the NMR chemical shift in selected organic compounds. In that saturated heterocyclic is also mentioned here. Sulfur based, nitrogen based, oxygen based. The electron density is calculated on the ratio of number of electrons and number of protons. This is the aromatic compound. This is the pi electron density for that propylium, etc. These are the chemical shift for this aromatic compound. Some list of substituent constants for estimating proton chemical shift of methylene and methylene protons. These are all the substituents here, R1 and R2 generally, that is called what? Substituents. It is calculated with the help of these substituent constant values. With the help of the substituent constant, we can estimate the chemical shift of given compound. The proton whose chemical shift has to be calculated can be primary, secondary or tertiary protons. The chemical shift of a methylene group attached to two substituents can be calculated by means of the substituent constant using the following equations. Delta CH2 is equal to 1.25 plus sigma 1 and sigma 2. We consider examples here. Methylene protons. We consider CH3, CH2, CH2O, benzene ring. That is calculated. Resonant frequency of methylene protons is calculated with the help of what here? 1.25 plus 2.3 plus 0.4, totally 3.95 for ppm. The result is in good agreement with the experimental data of 3.86 ppm. Next we consider chemical shift for the methane proton of the following compound is calculated from the delta values. Here delta CH is equal to 1.5, that is methylene, 1.2, 1.3 and nitro group it is what here 2.7. Like that we are going to calculations of this chemical shift. The ring current effect or diamagnetic ring current. The aromatic protons resonate at a field 122 ppm lower than olefinic protons. The low field shift of the protons directly bonded to an aromatic ring is caused by the circulations of pi electrons. The presence of a ring current is characteristics of all Eccles aromatic molecules and serves as an excellent test of aromaticity. Just to consider a benzene ring. When benzene ring, it is an aromatic compound, is placed in an external magnetic field. The pi electrons of the ring circulate around the ring and generate a ring current. This ring current in turn induces a local secondary magnetic field. These are schematic representations of aromatic ring current. Aryl protons are de-shielded by the induced magnetic field caused by pi electrons circulating in the molecular orbits of aromatic ring. This is called what? Shielding zone. This is what? The shielding zone. Here this leads to two current loops, one above and below the plane of the pi bond. The induced field opposes the applied field in the middle of the ring, but reinforces the applied field outside the ring. The ring current generated by the pi electrons is called the diamagnetic ring current. This ring current decreases the strength of the external magnetic field in the middle of the ring and increases the strength of the external magnetic field outside the ring. Here the benzene ring does not contain any protons in the middle of the ring or above and below the ring. All benzene protons are located in the molecular plane and outside the ring. Chemical shift of the aromatic protons therefore appear at low field. We consider examples of this. 1,6 methanoaniline has two types of protons. Protons attached to the ring and methylenic bridge protons located above the aromatic ring. The aromatic protons are de-shielded and absorb at a field lower than normal, means olefinic protons, and the methylenic protons are shielded and absorb at a field higher than the normal. This resonance appears on the right side of the tetramethylsilane signals. The methylenic protons are bonded to two vinylic groups as shown in the figure. This is what the structures. What is that? What is the value of this? 7.27. It means here 6.95. What about that? HC is what? Minus 0.5 ppm. The dianion of trans 10B, 10C, dimethyl dihydropyrene provides a striking example. The neutral compound, the signal of the methyl protons is found to be minus 4.25 ppm. In the absence of shielding effect of the ring, one would have expected a signal at delta 1 ppm. The aromatic protons in neutral compound resonate at 7.95 to 8.67 ppm. The methyl protons in dianion resonate at 21 ppm. The aromatic ring protons at minus 3.95 ppm. This is what? The dramatic shift differences between the spectra of the neutral and dianion compounds are observed. The neutral 14 pi electrons and it is an aromatic compound. It shows a strong dimagnetic ring current. By reductions of neutral compound with metallic potassium, it is converted into the doubly charged anion, which has 16 pi electron. This compound generates a strong paramagnetic ring current, as explained that above. Here. These are all the different annuals. This is 18 annual 6, 18 aniline 7, 18 aniline 8. These are the different examples are mentioned here. Here, this is chemical shift inside that ring. Sorry, outside the ring. This inner value. This is aromatic and bridged. This is olefinic and bridged, etc. These are all these some examples regarding to that what chemical shift. Next concept, the spin-spin splitting in proton NMR spectrum. We have seen that differences in chemical shift of protons are caused by small local magnetic field electrons that surrounded the various nuclei. Chemical shift is also affected by the magnetic anisotropy of different functional groups. For two protons bonded to an adjacent carbon atom as shown above, if different alignment of the magnetic moment of the proton B in the external magnetic field can affect the chemical shift of the neighboring protons HA. The direct alignment of the magnetic moment of the proton will cause fine splitting in the signal of proton. As a consequence, the number of signals in the spectrum will increase and the appearance of spectrum will be complex. At the same time, we will obtain more information from the spectrum of interpretations. Just to see here, this is proton NMR spectra of ethyl acetate and ethylene melanoate are shown in the figure here. This is what ethyl acetate. Not ethyl acetate. CH3 is common, this one. CH3 is common, this one. This CH3 is attached with O. That is what? This one. And CO. Just you consider these three examples. Ethyl acetate contains two different methyl groups, the chemical shift of which as expected are different. One methyl group is attached directly to the carbonyl group, the other to the methylene group. However, the appearance of the signals becoming to these methyl groups are completely different. While the methyl group that is bonded to the carbonyl group resonates as a singlet at around 2 pp. The other methyl group resonates 1.3 ppm as a triplet peak. The proton's other methyl group has two neighboring protons. We can conclude from this observation that the neighboring protons are responsible for the splitting in signals of the methyl group. Similarly, we consider some other examples of this dimethyl, diethyl melanoate, etc. The dimethyl melanoate, we observe similar signal splitting. The methylenic protons located between two carbonyl groups are equivalent and possess no neighboring protons, while their resonance signals appears as a sharp singlet at 3.2 ppm. The other methylenic protons next to the methyl group resonate as a quartet. Just we consider in that spin-spin splitting of single absorption peak into multiplets, either it is doublets, triplets or quadrets, arises from different number of neighboring protons. Conversely, the splitting in the resonance signal gives us exact information about the number of neighboring protons. This is a very important point in Nmr spectroscopy in regard to structural analysis. This phenomenon, signal splitting, is called spin-spin splitting. We consider examples for that. A proton is irradiated with electromagnetic radiation of the proper frequency. Energy absorption occurs and lower energy state flips to the higher energy state, means anti-parallel, which is called the resonance. Just we consider this, proton HA will be under the influence of an increased H1 and decreased H2 magnetic field, depending on how the neighboring protons HB is aligned. These magnetic fields are as shown in that figure. Where H total is what? Magnetic field influencing proton HA and HB in the magnetic moment of proton H2. Since proton HA will be under the influence of an increased and a decreased magnetic field, the HA proton resonance will occur at two different values, which is applied field. This phenomenon is called what? Spin-spin splitting. It's very important, spin-spin splitting. This is the spin-spin splitting of two coupled protons HA and HB, representation of the chemical shift and the coupling agent. Next we consider what are the spins of these two equivalent protons can be aligned in the three different combinations. Both proton spins can be aligned anti-parallel to the applied field. One proton spin can be aligned parallel while the other aligned anti-parallel to the applied field. Both proton spins can be aligned parallel to the applied field. When two proton spins are aligned anti-parallel to the applied field, the total effective field at protons HA is slightly decreased. In the second case, the proton is aligned with the applied field. The other one is against. These effects cancel each other. So the effective field at protons HA is the same as the potential field. The summary of the proton will be under the influence of three different magnetic fields as shown on that figure. H1, H total minus 2 UV. H2 is equal to H2 total H minus HB plus HB is equal to H total. H3 is equal to H total plus 2HB. Where H total is the magnetic field including the effect of the neighboring groups influencing the protons HA and HB in the magnetic moment of proton HB. These are all some examples are mentioned here. The populations of three different energy levels are reflected in the signal interest. The BB dash distribution ratio is 25, BB dash that is also 25, HB dash, HB and HB dash it is in 50. This is the energy level for the three different spin states of the methylene protons that produce triplet and distribution ratio of the magnetic moments in a magnetic field. The distance between the triplet lines must be equal, and this value in hertz directly gives the coupling constant JA between the coupled protons. The same coupling has to be extracted from the distance between the doublet lines of protons HB. In general, the two groups of protons coupled to each other must have the same coupling constant J. The inner line of this coupling are mentioned here. These are simple examples. Please we go through that by following the consideration. I am going to take an HA, HB, HC. These also some other examples of this here. Ether. CH2, CH3, CH2, CH. What happened here in that ethyl group, which is encountered very frequently in organic compounds. For example, diethyl ether has two set of equivalent protons, H2s and H3. Let us now apply the basic splitting constant, which we have already seen to the total ethyl group. We can predict that the methylene group will split into a quartet due to the three neighboring protons and the methyl protons into a triplet. Inspections of the proton Nmr spectrum of diethyl ether support our predictions. Next we consider this. By consider all other observations to summarize with the following the general rules here. The chemically equivalent protons do not exhibit spin-spin splitting. The equivalent protons may be on the same or different carbon atoms, but their signals do not split. Resonant lines are split by neighboring protons. The signal of a protons that has n equivalent neighboring protons is split into a multiplet n plus 1 peak. The relative intensities of the peak and multiplicity can be directly determined from Pascal triangle. The distance between the split lines are equal and they corresponding to the coupling constant between the coupled nuclei. This is what Pascal triangle. Number of equivalent adjacent proton is 0. It is having singlet. If 1, doublet, 2, triplet, etc. For 6, we are considered what septet. This is what Pascal triangle relative intensities and types of signals. With the help of these Pascal triangles, the multiplicity and the relative intensities may be easily obtained. We will demonstrate the appreciably of Pascal triangle with some selected samples. Let us consider from 1-bromopropane. This is a what? 1-bromopropane molecule. This is what? Only one. This is CH3 like that. Next we consider that Nmr spectrum of 2-bromopropane molecule. Just to go through that. Very important. What is that? Intensities and everything. Splitting observed, splitting not usually observed. These are all some other example. We go through that. Next I am going to explain that spin-spin coupling mechanism. That spin-spin coupling mechanisms. What happened? One is that parallel, anti-parallel, anti-parallel and parallel mechanisms. Okay. In that parallel and anti-parallel, before considering the factors that affect spin-spin coupling constant, let us discuss briefly the mechanism of spin-spin coupling interactions. How does spin-spin coupling rise? There are 3 different mechanisms that contribute to spin-spin coupling. According to this mechanism, spin-spin coupling between 2 nuclei A and B arises from the interactions of nuclear spin A and B, which involves the bonding electrons connecting these nuclei. For example, hydrogen and carbon molecule 2 atoms are bonded to sigma bond having 2 electrons. The coupling mechanism for the proton-carbon coupling can be visualized as follows. According to that Pauli's principle, 2 electrons in the bond between the nuclei must have their spin paired. Therefore, the magnetic moment of the second electron adjacent to carbon 13 will have an orientation parallel to the applied field, which will force the nuclear magnetic moment of the carbon atom C13 to align itself. This is what anti-parallel. When this all is in that same direction, that is what anti-parallel. The schematic representation of the spin-spin interaction, proton-carbon through bonding electron in carbon-hydrogen bond. The anti-parallel orientation of proton will force carbon atom to align itself in parallel orientation to the applied field in the same manner. Consequently, the magnetic field around the resonating molecules will be affected by the orientation of the adjacent nucleus. In this particular case, the nuclear magnetic moment of one nucleus forces the nuclear magnetic moment of the other nucleus. In the second case, discuss coupling through two bands, geminal coupling. For example, we analyze the orientation of the nuclear moments of the nuclei and the magnetic moments of electrons in the structure. These are all same thing. Previous one, this is parallel mode. We consider the next coupling is viginal spin coupling, which can always be encountered in Nmr spectra and provide very useful information for the determinations of the chemical structure. By applying the same models discussed above, we see the nuclear magnetic moment of one atom. One nucleus forces the nuclear magnetic moment of the coupled nucleus to orient itself in the opposition direction. Therefore, most viginal coupling have a positive sign. What are the kind of information gathered by measurement of coupling constant? This is also one of the very important. A distributed carbon-carbon double bond can have three different isomers, trans, cis and geminal. The measured coupling constant between the protons bonded to the carbon-carbon bond can determine the exact position of the substituents. Benzene ring having more than one substituent, the number of isomers depends on number of substituents. The exact location of these substituents can be easily determined by measuring the coupling constant between the protons, which are attached to the benzene ring. During chemical reaction, the configuration of isomers such as exo or endo or syn or anti can be formed. Again, coupling constants can distinguish in most cases between these formed isomers. Through the analysis of an unknown compound, the geminal coupling constant can provide some idea about the size of the ring. In addition, the dynamic process existing in the compound can be studied with the aid of coupling constant. Even the dihedral angles between the coupled nuclei and the bond distances can be determined approximately by the coupling constant. To summarize this, the coupling constant provides us with information about the constitutions, configurations and conformations of the molecule. The coupling constant between the nuclei are denoted by Z. Number of bonds between the coupled nuclei is indicated by a superscript N, which is given the left hand side of NZ. The coupling constant between the nuclei is denoted by subscript and is given on the right hand side, N into ZAB, N into Z1. The different coupling constant observed in organic molecules. We consider N is equal to 1, the proton Nmr spectroscopy. Only one molecule exists for this special case, which is hydrogen molecule. The coupling between the hydrogen atom and is of only theoretical interest. When N is equal to 2, the number of bond between the coupled proton is 2. these protons are bonded to the same carbon atom, and the coupling is called geminal coupling. Geminal coupling can be observed between the protons of a CH2 group, provided that they are economically equivalent. The third one, n is equal to 3, the number of bonds between coupled proton is 3. The commonest and most useful coupling encountered in proton Nmr spectroscopy is called visional coupling, which is denoted by J3. This coupling is observed between adjacent protons. The bond between the carbon atoms can be single as well as double bond. A double bond is encountered as a single bond. This visional coupling, if n is equal to 4, we are going to take n is equal to 5. Next, we'll move on to that geminal spin-spin coupling. In that geminal spin-spin coupling constant, Z2 range from minus 22 plus 40 Hertz. There are 4 structural features that affect the geminal spin-spin coupling constant. One is the dependence on the hybridization of the carbon atom, dependence on the hydrogen bond, thermal effect of the substituent, finally the effect of the neighbors by substituents. What is the dependence on the hybridization of the carbon atom? The geminal spin-spin coupling constant strongly depends on hybridization of carbon atom bearing the coupled protons. These are all the example of that. What is the dependence on that bond angle? The increase in the angle HCH causes very important changes in the geminal proton coupling J value. In cyclic system, the bond angle depends on the strain of the ring. Therefore, the measured geminal coupling constant in the cyclic systems is a measure of the ring strain. In other words, the ring size such as cyclohexane and cyclopentane molecule. What is the bond angle here? HCH psi is close to the angle in methane. Therefore, the geminal coupling observed in 5 and 6 membered ring is close to that of methane. When the ring is decreased, the bond angle is increased. The greater the bond angle between the coupled protons and the more positive the geminal coupling J. These are some examples. Geminal coupling with respect to chemicals. What are the effect of substituents here? The geminal coupling constant are subject to the influence of both alpha and beta substituents. These electronegative substituents directly bonded to the methylene groups causes a positive change in the coupling constant. These are all some coupling constant are mentioned here. Just to see here, methane, chloroform, etc. Now we are going to find the electronegative effect of substituents on the geminal coupling can also be observed in the unsaturated system. In ethane, the geminal coupling is 2.5 Hertz. However, the formaldehyde as coupling constant is 41 Hertz. The effect of neighboring pi substituents. One of the most important effect influencing general coupling constant is the number of neighboring pi bonds directly attached to the methylene carbon atom. This effect of the pi bond has to consider separately in two different systems. One is that acyclic system and cyclic system. These are all some other examples for that, cyclic systems and acyclic system. Next, regional spin-spin splitting. The most useful and informative coupling encountered in NMR spectra is regional spin-spin coupling. The regional coupling, the number of bond between the coupled protons is 3. Let us consider the following in olefinic compounds. There are two different initial couplings. In ethylene and ethylene derivatives, these coupling are different and the coupling between cis proton is smaller than the trans protons. These are all some very important positive. Depends on what? Torsional or dihedral angle, the valence angle, bond length and electronegative effect of the substituents. This was dependent on the dihedral angle in Corplex equation. What is that Corplex equation? This is J square is equal to J cube is equal to 4.22 minus 0.5 cos theta plus 4.5 cos theta. By using this formula, we are going to calculate that. These are all relevant for that. Some applications of this NMR dependent on the valence angle theta. Another important factor influencing the regional spin-spin coupling is the valence angle CCH theta. The dependence on the bond length, the pi bond order, another important parameters influencing regional spin-spin coupling is the distance between the carbon atoms bearing protons. The coupling decreases with increased bond length. Since carbon-carbon double bonds are shorter than carbon-carbon single bonds, the regional coupling observed between double bond protons are larger than those of saturated systems. The substituent effect. This is the long range coupling constant. In that long range coupling constant, proton-proton coupling behind two bonds J and three bonds I3. It also observed very frequently in organic compounds. These couplings are called long-range coupling. The appreciable long-range coupling may occur in alkenes, alkynes and aromatic systems, which gives very important information about the system of pattern. We consider the important long-range coupling categories are mentioned below. Allylic coupling, homolytic coupling, proton-proton coupling in benzene as derivatives, coupling in cyclic systems. This is allylic coupling. These are some examples are mentioned here. Just you go to that is homolytic coupling, same thing. This long range coupling in saturated system. Finally, we are going to do here summary of that unit. Dear children, Students, the NMR or nuclear magnetic resonance spectroscopy is a technique used to determining the compound spinning structure. It indicates carbon-hydrogen framework of an organic compound, even though there are many other spectrometers include NMR and carbon NMR and nitrogen NMR and hydrogen NMR. But first and is the most common atom is used in the nuclear magnetic resonance spectroscopy. The energy difference between the two spin states of the nuclei depends on the applied magnetic field. The greater the strength of the magnetic field, the larger the energy difference between the two spin states. When radiation that has same energy is placed upon the sample, the spin flips from alpha to beta spin states. Then the nuclei undergo relaxation. Relaxation is when nuclei return to their original state. In this process, we emit electromagnetic signals whose frequencies depends on E as well. Just each group of chemically equivalent proton gives rise to a signal. Chemically equivalent protons are protons that are in the same environment and they must be identical in every way. The experience is the same magnetic force and therefore will create overlapping signals on the spectrum. The position of this spectrum will explain that everything. The conclusions means here the splitting of signal is caused by the protons bonded to adjacent carbon. Different spin flip energies for HA to the different protons of that HP signals parallel. HA feels a stronger field and they are anti-parallel. Okay. These are all some keywords are mentioned here. Just you go through that, all the questions. First you make it into a notes for this. Discuss populations of energy levels. First you are going to make that notes. Then it is helpful to that your examination. There is a briefly explain that NMR instrumentation that is important chemical safety. Discuss the unit of chemical safety. Spin-spin coupling. Spin-spin splitting. These are all important. And discuss briefly affect the geminal coupling. Vicinal spin-spin coupling. Vicinal spin-spin coupling. Some important effect. Discuss the effect of the following on chemical shift. Dependence on the dihedral angle, dependence on the valence angle, bond length, substituents effect, and discuss the following that allylic coupling, homo-allylic coupling, proton-proton coupling. These are all very important. What questions we mentioned in that end of the unit? Just you go through that questions with answer. First you are going to make that answer. Then it is very easy to read. Okay. Thank you.